Good morning, everyone. I'll be talking about rabbit mix. This is joint work with Chongwon, Sam Dittmer, Yuval Ishai, and Rafail Ostrovsky. Okay, so let me sort of set the stage here, right? This is about anonymous broadcast. And imagine you have a set of senders, a set of receivers, and the senders have messages they want to send. And the goal is to have all of the honest receiver receive all the messages from all the honest senders. In other words, broadcast. Okay, but we want to do this in the presence, right, potentially of adversaries. Adversaries, they sort of can't interrupt honest participants. We want to make sure that they can't link messages, right? So what kind of system do we need to build to guarantee those kinds of things, right? Guarantee that we have an anonymous broadcast in the presence of these adversaries. Now, of course, looking at this problem, there are plenty of main approaches, right? I think there's a very common approach of onion routing, of mixing networks. But the topic for today, we're going to focus on the secure multi-party computation-based mixing networks. There have been a lot of research along these lines, Riposte, Blinder, and so on. And I'll be sort of talking mostly about this line of work. So now, of course, there's definitely trade-offs between the onion routing and mixing approaches versus the MPC-based approaches. The sort of main thing to sort of highlight, right, is that there are very sort of clean cryptographic or algebraic guarantees of non-linkage, and we have and the sort of the security is inherited from the security of the MPC. It's a little bit trickier to set up, admittedly, but we'll see how great it is and what it can do in just a bit. Okay, and there's also potentially a lot of applications for this, reporting, whistleblowing, journalism, so on and so forth. But let me go ahead and first define formally the setting, right? And this is the setting of robust anonymous broadcast, right? Where you have, and this is in the MPC setting, you have capital N clients, and each client has a message. You have little n servers, and the clients submit these messages to the servers. What we're going to actually do here is actually going to secret share them. And the n servers, the little n servers, are going to run an MPC protocol to actually do this mix, and then return the messages, the mixed messages to the clients. And we want to have things like small round complexity between the servers. We want to have sublinear communication, and I'll say what sublinear means in just a second, from clients to servers. And we want to have a small chance of delivery failure, and also enable efficient sort of offline computation, right? Because you can think of secure multi-party computation having an offline phase as well. And a lot of times you can just shove a lot of that computation offline. We want to keep it sort of balanced, right? Where the offline time and the online time is roughly the same. So let me just first quickly review some of the previous works. Think about private writing in like a riposte model, right? Where you have essentially you have a message X and you want to write it into this big array. And it's super helpful to actually think of this array as a two-dimensional sort of grid, because what you can do is you can essentially just write this in a decompressed way, or a compressed way, I guess, as a tensor of two vectors. And what this will give you is you can now essentially just throw things into these buckets. And the reason for this is you want to be able to compress the amount of information that the client sends to the server. So this does get a little bit bigger, but the overall point is that you can extract these messages. They remain anonymous, and the amount of information the client sends to the server is 5 root n, where n is the number of clients, right? So when I say sublinear, I meant sublinear in the number of clients. The server computation is n squared. Basically, for each client, you have to do one of these things. Just due to a counting argument, you can get about 95% of the messages through, right? But what if we wanted to get more of the messages through, like 99%? Turns out, if you just work through the combinatorics, you need to be bigger by a factor of 22 to get to like 99.9. So there is this kind of issue with scaling here, and how have other works attempted to solve this? So there's another approach through power mix using Newton's identity. This approach allows you to essentially gather up not just your messages, but if you gather up also powers of your messages. When they add up, you can actually extract back the original ones if you have the right sets of powers, right? So I'll talk about just that in just a second, right? But basically, you send every single power 1 to n, and then if you actually have all of these, you can actually then use Newton's identity to convert sums of powers into a symmetric polynomial and then back into your original messages, right? It takes a little bit of work to do, but you're able to do this. Okay, well, great. Now the client just has to send one, something of size 1, but now the server computation balloons to n cubed, right? And it's good in the sense that you have all your messages being correct, but now the server work has gone up, right? So the question is, can we get the best of both worlds, which is highlighted in blue here, right? Can we get sort of low client communication? Well, maybe not as good as 1, constant, but sublinear. Still have quadratic server computation instead of cubic, and still get the 100% of messages being correct without having the space being blown up. So the approach is we call rabbit mix, right? And this is really the goal, right? The two goals, or I guess the three goals, are 100% message delivery rate, and also sublinear communication from the clients, sublinear again in the number of clients, and the server computation being quadratic, right? And our approach here is an additive two basis. So let me kind of explain what that is, right? Imagine you wanted to make change for, like, I don't know, any number between 1 and n, right? If you have, let's say, American coins, if you wanted to make change for, let's say 50 cents, okay, that's 2 quarters. 30 cents, okay, a quarter and a nickel. 31 cents, okay, well, you can't do that with 2 coins, right? And so the question about additive two bases is, if you wanted to make change for any number between 1 and n, and you only get 2 coins, right, 2 coins, what denominations of currency must you have? Very interesting combinatorial problem. And so let me just give like a flavor for a silly solution, right? Which is, okay, suppose I have like a 1 cent coin, a 2 cent coin, all the way up to a 9 cent coin. And then I have a 10 cent coin, a 20 cent coin, all the way up to a 90 cent coin, right? It's obvious here that if you have this, you can make change for anything up to $1. And the point is that this naive thing already kind of gives you a square root solution at the cost of 1 multiplication, right? If you can sort of if you multiply two of these things, you get their exponent sum together, and then you can now sort of build every single possible power from like 1 to n, right? And if you have every single power from 1 to n, then you can do this sort of Newton's identities trick, and then get your answer. Okay, and of course, as it turned out, there's actually better additive two bases that you can use. For example, if you just look in the works of combinatorics, you can find one that goes from like 2 root n down to like 1.87 root n. And if you look at the cost of this is already 3x better than something like Blender that takes this approach, but then does not have this sort of additive two bases built in. Okay, so what does this look like? Well, okay, so the clients now have to send, right, all these sort of denominations, 1 through 9, and then 10, 20, 30, all the way up to 90. And then what does the server do, right? Well, the server can now, again, compute all these things, but now it's just 1 multiplication each instead of n multiplications each. And then that means that overall, if you consider all the clients together, that only takes n squared. After that, we still do once we have the powers, the sum of the powers, still do the sort of the existing trick of extracting essentially the roots of those polynomials. Again, right, using Newton's identity. So that that essentially solves the problem, except we're not quite done yet, because what about malicious clients? Right, they can lie about their denominations, right? What if they lie about, let's say, x to the 9? I give you something else that's bogus, right? What do you do there? Well, it turns out, right, you can essentially do the same kind of check as if you were actually building these things, but it's not entirely sort of. It's not obvious that what you have is or isn't enough. It turns out that just because you can make any change doesn't mean you can also verify any change, right? And there's some very interesting sort of examples there. But turns out that if you build your additive two bases in a way that not only can you build any sort of denomination, but also check against them, you can essentially do this kind of linear sketch for these additive two bases. And with that, then you can not only construct all these powers, but you can also check that each one of these green sort of currency pieces are actually correct, right? So you have that verification as well. And with those two things combined, now the client can't cheat. Then you can actually get that robustness against potentially malicious client behavior. Okay, so putting all this together, right? We built a proof of concept. We brought in the NTL library to do all of the sort of interesting sort of number theory to help find roots and such, mod P. We just used like an off-the-shelf Boost library for networking. We didn't attempt to parallelize this. This is very, very amenable to parallelization. We didn't try doing that. And we test this using 5 servers and a bunch of clients emulated on a single client machine. Okay, so the results, right, essentially are that you see that the end-to-end latency actually isn't that bad, right? So for something like the number of messages to be mixed or the number of client messages, these things essentially grow linearly, as the size goes up, right? But perhaps more interestingly, let me sort of show you the amount of time spent in all the various subprotocols. When you're sending things on the order of, when the number of clients, right, is something like, from 500 to the 1,000 to maybe even the 10,000 range, you're spending actually a lot of time doing the root finding, right? So actually the mathy portion is actually really your bottleneck. But then you see as you go into like the 20,000, 30,000 client range, things become a little bit more balanced, right? The time it takes to do all these things, Callan balances out. And let's say, for example, if you had 32-byte messages, how much do the servers have to talk to each other? And essentially that also kind of grows linearly, right? We're talking something on the order of megabytes. And just to make sure everyone's paying attention, right, that crazy kink in the graph is only there because if you look at the x-axis, we go essentially linearly up to like 10,000, and then we did 2 more big tests after that. We put them on the same graph, so really there's like a disconnect there, a discontinuity there. Okay, so there's that, and again, client communication, we expect this to be sublinear, and then comparing this to something like the previous work, Blinder, right? We're getting, like we said, about a 3x savings. Okay, so with that, I will wrap up and basically just sort of summarize what we did, right? We created a new anonymous broadcast protocol in the MPC model where we're able to do mixing with about a 3x improvement to Blinder and other sort of private writing-based protocols. And we had a nice implementation, and this is based off of something called additive two bases, and that is the gist of my talk. So thanks a lot, everyone.